we were looking at the infinitesimal generator of a C0 semigroup, and our next result is crucial for the study of evolution equations in the framework of C0 semigroups. So, theorem: V Banach ST a C0 semigroup on V. A its infinitesimal generator. Let U belong to D of A. Then S dot U, that means T going to ST of U, belongs to C1 of 0 infinity with values in V, and it's also continuous from 0 infinity with values in D of A. Remember, D of A is a Banach space with the graph norm. So, you think of that way. So, if you take T going to ST of U, it is continuously differentiable when you think of it as values in V, and it is continuous. It means this STU actually belongs to D of A for every T, and mapping going to T going to ST of U is continuous into the dA, that means with the graph norm. Okay. And d by dt of ST of U equals A of ST of U equals ST of AU. U in dA, remember that, only then. Okay. So, proof: U belong to dA. So, we want to show that ST of U belongs to D of A, because that is part of the problem, and then because we also have it in the statement of the theorem, A of STU, etc. And therefore, we compute, see if it, so SH minus I by H acting on ST of U, see if this limit exists. Okay. So, this is nothing but ST of SHU minus U by H. Okay. And now ST is a continuous linear operator. SHU minus U by H, by definition, since it is in the domain of A, it goes to A of U. So, this goes to ST of A of U. Therefore, this implies, that means this limit always exists. So, this means that ST of U belongs to D of A, and A of ST of U, which is the limit of this, is nothing but ST of AU, and that is equal to, of course, since we are taking SHU minus U by H, so this is nothing but D plus of ST of U. So, this is a forward derivative. So, now you consider ST of U minus S of T minus H U divided by H, and that is equal to S of T minus H of SH of U minus U divided by H. Okay. So, therefore, you have ST of U minus S of T minus HU by H minus ST of AU equals S of T minus H of S of HU minus U by H minus AU plus ST minus H minus ST of AU. Okay, simply added and subtracted something. So, now let us look at the first term, norm of S of T minus H of SHU minus U by H minus AU. So, this norm is less than or equal to m e power omega t minus H, okay, into norm of SHU minus U by H minus AU. Now, this, as H goes to 0, this goes to 0, as h goes to 0, because u is in domain of A and AU is precisely this limit. So, this goes to 0 and this can be bounded, and therefore, this goes to 0. Okay. And so, this is because u is in D of A again, and norm of S of t minus h, we have already seen this, minus S of t of AU goes to 0 because of the continuity of t going to St of AU, that we have already seen the continuity for any vector, and therefore this means that this limit here exists and the limit is equal to St of AU. So, d minus of St of AU equals St of u is St of AU, which is also equal to d plus of St of u. Therefore, so this implies d by dt of St of u exists and is equal to St of AU, which also we saw is A of St of u. So, that proves this. Now, we know that t going to St of AU is continuous. This implies t going to St of u is C1. Okay, it is already continuous and this derivative is t going to St of AU, and therefore that is also continuous, therefore it is equal to C1. And you have St of AU, St of u belongs to D of A, and you have that t going to St of AU is continuous, and therefore and St of derivative is nothing but A of St of u, and therefore so t going to St of u and t going to A of St of u continuous because of this relationship here, and therefore that implies t going to St of u is in C of 0 infinity with values in dA. Okay, so therefore you have, because the graph norm has been that. Okay. So remark, we have that A commutes with St. on dA. Okay, that is important. So what have we shown? We have shown that u dash t equals A of ut, t going to 0, u of 0 equal to u0 if A is the infinitesimal generator of a C0 semigroup S of t, then above initial value problem has a solution, namely ut equals St of u0. It satisfies the thing. Provided u belongs to D of A, u0 belongs to D of A. So, you can solve this equation. If A is the infinitesimal generator of a C0 semigroup, then this initial value problem, where the initial data belongs to the domain of the infinitesimal generator, can be solved, and you have a classical solution of this initial value problem, namely you have a C1 solution here which satisfies this equation. So, if u0 is not in dA, then St of u is not differentiable, and we say ut equals St of u0 is a generalized solution of the above initial value problem. So, we also have uniqueness. So, you write, suppose I have V is another solution, possible solution of the IVP. Okay. So, then we put W of S equals S of t minus S, S of Vs. Then what is W dashed of S? Then you can check. So, check, we have to, it's a very easy checking. So, we can do it anyway. So, we apply the product rule. So, when I apply the product rule, so we have, that means VFS. So, this implies that VFS is in DFA, because otherwise we can't be a solution for the initial value problem, because du by dt equals AVT. So, V must be in domain of A. So, V is in domain of A. So, if you differentiate with respect to S, so you will get S of t minus S V dashed of S, plus you have VFS is here, differentiate S of t minus S, you get minus S of t minus S A V dash V of S. Now, A V of S is V dash of S, and therefore this is equal to 0. So, that means W of t equals W of 0 for all t. And what is W of 0? That is nothing but S of t. So, W0 equals S of t V0, which is equal to S of t U0, okay, which is equal to U of t, okay, and that is equal to Wt, which is equal to, if S equals t, it is just V of t. So, U of t equals V of t for all t. So, that means the solution is unique. So, we have a unique solution provided the domain. So, if we want to investigate initial value problems of the form u dash t equals A of u, so u dash t equals A of u t, u of 0 equals u naught. So, then we must know when is A the infinitesimal generator of a C0 semigroup. So, we want to recognize those things. So, if we know that A is the infinitesimal generator, then we can write down the solution at least when u0 is in domain of A explicitly, and then we can write down generalized solution if u0 is not in the domain of A, and therefore we can solve this problem in some way or the other. Therefore, we have to know when is A the infinitesimal generator. So, we would like to give necessary and sufficient conditions for unbounded operator to be the infinitesimal generator of a C0 semigroup. So, we will work towards that. So, theorem V Banach A infinitesimal generator of a C0 semigroup on V. Let U belong to V. Then we know that t going to st of u is continuous, and therefore you can integrate it. So, 0 to t s tau of u d tau belongs to d of A. Now, if u is in d of A, then st of u is already in d of A, we know that. Now, if u is not in d of A, u is any element of V, st of u will not be in d of A, but the integral of st of u over 0 to t will belong to d of A, okay, for all t positive. And so, once it is in d of A, we would like to know what is the action of s tau of u, action of the operator A, and that is equal to nothing but st of u minus u. So, very beautiful result. Okay, so proof. So, let h be greater than 0. So, we just have to check whether that integral is in this thing. So, by h acting on integral 0 to t s tau of u d tau. Now, what is the property of the integral? How is the integral defined? It means that every continuous linear functional, every continuous linear mapping can pass through the integral sign. That is what we have in the definition of the integral itself, and built into the definition of integral if you have seen it already. So, this is equal to integral 0 to t s of tau plus h u minus s tau of u d tau 1 over h. Now, we will make a change of variable tau plus h equals tau. So, this will become h to t plus h. This integral will become h to t plus h. Then you have s tau of u from t to t plus h minus s tau of u from 0 to t. So, if you simplify this integral, you will get integral equal to integral t to t plus h s tau of u d tau minus integral 0 to h s tau of u d tau. So, it's just elementary thing. You make a first change a variable for the first one, make it integral s tau of u, and limits will change from h to t plus h. Then you have two different limits, and so then you compensate, and then you will get this thing. Now, we know the limit of this 1 by h of integral something is nothing but the limit as this goes, as h decreases to 0. We know it should go to the lower limit. So, this goes to st of u minus this will go to the lower limit which is s0 of u, which is u. Therefore, so this implies that integral 0 to t s tau of u d tau belongs to d of a and star holds. So, corollary, if A is the infinitesimal generator of a C0 semigroup, then A is closed and densely defined. So, now already the importance of closed and densely defined operators comes up, because this is a necessary condition. It is not yet a sufficient condition for the infinitesimal generator to give a C0 semigroup, but we have at least we have to, where do we look for the infinitesimal generators? We have to look only amongst closed and densely defined operators. Okay, so proof. So, let u belong to V. So, we want to show that dA is dense. That means we can approximate u by means of elements of dA in the thing. But then we just saw, but integral 0 to h s tau of u d tau belongs to d of a, and therefore 1 by h of this also belongs to d of a, okay, and then this converges to u, and therefore implies dA is dense. Okay. So, now we want to show that it is closed. So, let un in d of a such that un converges to u in V, and aun goes to some V in V. So, to show u belongs to the domain of A and AU equals V. So, that is the meaning of A being closed. So, we just have to, there is no other way to do, SH u minus u by h. So, we have to compute this as h goes to 0. Now, this is equal to limit as n tends to infinity SH of un minus un divided by h, because un goes to sh is a continuous linear operator and un goes to u in B. So, this is equal to 1 by h, sorry, limit n tending to infinity 1 by h of integral 0 to h d by dt of s tau un d tau, okay. Because if you are integrating d by dt, then it is just the difference of the end values. So, sh un minus s0 un is un. But what is d by dt f tau? Un is in d of a, you remember un is in d of a, and therefore this is equal to limit n tending to infinity 1 by h integral 0 to h of a of s tau of a un d tau. But then this limit we know is nothing but 1 by h integral 0 to h s tau of a un goes to v, and therefore this is equal to dv. So, you now take the limit. So, limit of sh of u minus u divided by h as h goes to 0 is equal to limit as h goes to 0 of 1 by h integral 0 to h s tau of v d tau, which is equal to v, and therefore this implies that u belongs sh of u belongs to d of a, and au equals v, and therefore it is a closed and densely defined operator. Okay, so we will now presently see what other conditions are needed for to be satisfied, which are necessary and sufficient for a unbounded operator to satisfy in order to become the infinitesimal generator of a C0 semigroup. That will be the next thing, but before we conclude today, so we have one more. So, if theorem. If two semigroups have the same infinitesimal generator, then they are identical. So, infinitesimal generator to C0 semigroup is a one-to-one correspond. Given a C0 semigroup, you have an infinitesimal generator, and if you have a unbounded operator which qualifies to be an infinitesimal generator for C0 semigroup, then there is only one C0 semigroup which it can generate. It can't generate more than one. Therefore, for instance, if you have S1, so proof S1 of t, S2 of t, C0 semigroups having the same infinitesimal generator A. Okay, so now we set as before Ws equals S1 of t minus s and S2 of s u in d of a. So, this will be well defined, because if u is in d of a, S2 of s will be in d of a. So, S1 of t minus s of that is still defined, and then you can differentiate it because it is in d of a. So, this will be equal to, if you again we have to check, so check again, okay, the product rule will apply. So, this will be minus a S1 t minus s S2 of s u plus S1 of t minus s, differentiate S2, you get A of S2 s du, but A commutes. So, this is equal to minus a S1 t minus s S2 s of u plus a S1 of t minus s S2 s u, and therefore that is equal to 0. So, again W is a constant. So, W0 equals Wt for all t. W0 is, that is S1t, S2s is identity u equals, and if you take Wt, S1 of 0 is identity, so you get S2T of u for all u in DFA, and then DFA is dense in V because it is an infinitesimal generator, and therefore we have S1T of u equals S2T of u for all u in V. Okay, so they are one and the same. So this proves that the so we have now come to the following stage. We are interested in solving u dash t equals a of ut, t positive, u of 0 equals u0. So if we know that A is the infinitesimal generator of a C0 semigroup ST and u0 is in the domain, then we have a classical solution for this, namely ut equals ST of AU, and so we are interested in identifying those unbounded operators which are infinitesimal generators of C0 semigroups, and as a starting point we have said the necessary condition for this is that A has to be closed and densely defined. So we will now explore this thing further, and that will finally lead to the Hill-Yoshida theorem, which completely characterizes those unbounded operators which generate C0 semigroups.